Alright, in this video I'm going to talk about current and resistance. So the basic idea of this chapter, of this video, is to give you an idea of how and why current flows in a conductor. So we're going to start this discussion by taking a look at a capacitor. So a capacitor has two plates, one is positive, one is negative. And what we're going to do is connect a wire to the positive plate and another wire to the negative plate. Now, knowing the properties of conductors, we know that the charges from the positive plate, some of them are going to drift into the wire on the left, and the negative charges also. And the inside of these wires is going to, after the charges are done moving, the inside of these wires will have a zero electric field, because any conductor in equilibrium has zero electric field inside. So this is a very short amount of time when the charges from the plates are going to move to the wires, and as soon as that is done, the electric field inside those wires is zero. Now the interesting thing that's going to happen here is when we connect the two wires. So if the two wires are now touching, notice that at the point of contact we have positive and negative charges together. So as you know, positive and negatives are going to cancel. So the charges in the middle are going to cancel, and positive and negative charges are going to move towards each other. And for a period of time, we're going to have this flow of positive and negative charges, and they're going to encounter in the middle, and they're going to cancel in the middle. So the result of this is that the wire that connects the positive and the negative plate is going to have a non-uniform surface charge density. Remember that these charges are going to be on the surface of the conductor, but the interesting thing is that the distribution of the charges is not uniform. There will be more positive charges at the point of the wire that is closer to the positive plate, and as you move along the wire, the density of positive charges is decreasing until you get to the middle where the density of charges is zero, because that's the point where they're canceling out. And as you continue moving, then the density of the negative charges is going to increase until you get to the point of maximum surface charge density on that wire, which is the point that is connected to the negative plate. Now if we stretch that wire and we take a look at what's going on inside of it, we notice that if we were to consider two segments of the wire adjacent to each other, and we'll notice that each one of these rings is producing an electric field in the middle, in between them. Those two rings there are going to produce an electric field. The ring on the left is going to produce an electric field away from it. So that electric field, I'm calling it E left, and that points to the right. And the ring on the right, the ring of charge on the right, is going to produce an electric field that points left. But notice that those two electric fields are not equal in magnitude, because the charge on the left ring is bigger than the charge on the right ring. That's because the surface charge density is different, and the ring on the right, the surface charge density is bigger towards the left of the wire than towards the right. So any two rings that we consider, any two sections of the wire adjacent to each other, will have the same property. One section of the wire will produce, let's say, the ring or the section that is to the right, negative density of charge between those two. The one on the right will produce an electric field that points right, and the ring on the left has less density of charge, therefore less charge, and that one would produce an electric field going to the left. Those two electric fields are opposite to each other, but one is bigger than the other, so we get a net electric field at that point in the wire. So the result of this non-uniform surface charge density is that all throughout the wire, those surface charges produce an electric field inside of the wire. Now this is the key electric field that is going to produce a massive movement of charge inside the wire, because remember that a conducting material is full of conduction electrons, is full of electrons that are free to move wherever they want. So if you apply an electric field to those electrons, they will move. The electrons, because they have a negative charge, move in the direction opposite to the electric field. So every single electron, conduction electron inside of that wire will move to the left in this picture. Now, let's take a look at how that motion of the electrons actually is going to happen. Because an electron that feels a force to the left will accelerate, but remember that the electrons are not the only things that you find inside of a wire. A wire has atoms, and those atoms are going to have, the electrons are going to have collisions with those atoms. There's also atoms of the material, there's also impurities. So the collision between the electrons and the atoms and the impurities inside of the material result in a couple of things. One is scattering. The electron is going to change direction. It might accelerate to the left for a while, but as soon as it has a collision, the collision can potentially send the electron scattered in any direction. That collision is also going to take some of the energy, absorb some of the energy of the electron, and leave that atom vibrating faster than before. So as the electron moves through the material and experiences multiple collisions, the direction of the electron motion is changing, but overall, remember that every time the electron is between collisions, it's accelerating to the left in this picture. Overall, despite all of these collisions, the electron slowly makes it to the left of the wire. So, as we said, these collisions transfer kinetic energy that the electrons are gaining from the electric field, and is transferring that kinetic energy to the lattice of atoms that make up the wire. So that means that the wire is going to warm up as the electrons move through the wire. In general, you can say that a current moving through a conductor will always warm up the conductor. Now this, as I said, this sort of random motion of the electron as it's been scattered by the atoms and impurities inside of the wire, nevertheless, overall has a constant velocity. The electrons move in the direction of the electric field. They do it slowly, but they do move. That velocity is called the drift velocity, V sub d. Now, this motion of the electrons and the fact that there's so many of them, this motion of the electrons, this sort of random motion of the electrons, when considered in a statistical sense, gives us a result that the average drift velocity of the electrons moving through the wire is equal to the acceleration of the electrons multiplied by tau, Greek letter tau, which represents the mean collision time. That is, the average amount of time between collisions. So, given that the acceleration on those electrons is due to the electric force, then this acceleration is going to be the electric force, charge multiplied by the electric field, divided by the mass of the electrons, multiplied by tau. That gives us the drift velocity. Notice how the drift velocity, if we look at these quantities as vectors, we see that the drift velocity vector is opposite to the direction of the electric field vector. Now, an interesting question is, as these electrons move through the wire, is how many electrons cross a particular section of the wire per unit time, per second. Is it 5 electrons per second? Is it 5 million electrons per second that are going to be crossing that area? So the quick answer to the question of how many electrons cross that section A per unit time is that the number of electrons that cross that area is equal to the number of electrons that you can find inside that volume. The volume, denoted in the picture, is the volume of a cylinder with an area, with a base A and a height Vd times delta T. Now, why is that? Why are we saying that all of the electrons inside of that volume are going to cross the area A in an amount of time delta T? The answer is that it is so because if you start counting time, if you start your stopwatch at a particular moment, then the first electrons that are going to cross that area are the electrons that are right next to the area. Those are the first electrons to cross. The last electrons, delta t seconds later, when you stop the stopwatch, the last electrons to cross the finish line are going to be the electrons that were a distance Vd times delta t. Those are the last electrons. So the total number of electrons that crossed in that amount of time delta t is all of the electrons contained in that volume. So how many electrons are there inside of that volume? Well, it turns out that the density of electrons, of conduction electrons inside a conducting material is fairly constant. So electrons, in that sense, behave pretty much like a fluid, like a liquid flowing inside of a pipe. So as you know, liquids are not compressible. It's very difficult to compress and change the density of a liquid. So it is also true that the density of the conduction electrons is fairly constant as they move through the wire. So because of that, the number of electrons that fit inside of that volume is proportional to the volume, and the quantity n sub e is called the electron density. It is a fairly constant number, as I said, and it depends on the material that the wire is made of. So different materials will have different electron densities. Usually the conducting material has one conduction electron per atom. So that means that the density, the electron density is or can be obtained from the density of the material. It is the number of conduction electrons per cubic meter of the conductor. Now, we just said that the total number of electrons that are going to cross that area A in an amount of time delta t will be the electron density, N sub E, times Vd times delta t times A. So from here, we can easily get what is called the electron current. That is the number of electrons per second that are going to be crossing that area A, the number of electrons per second. So the electron current, lowercase I, is the N is equal to the total number of electrons that we figure out divided by delta T. And if you put the expression for capital N that we have just above, we see that when we divide by delta T cancels, and we have an expression for the electron current is Ne Vd times A. This is number of electrons per second flowing through this wire. Now from the electron current, we can get another current, which is perhaps even more important, which is what we call the charge current. From this point on, we're going to be using this quantity in electric circuits, or we're just going to call it the current. But it really, its full name will be the charge current. So since every electron carries an amount of charge minus E, where E is 1.6 times 10 to the minus 19 coulombs, then the charge current flowing through this wire is going to be minus E times the electron current. And if we replace the equation for the electron current, we get that the current flowing through the wire is minus E N sub E Vd times A. This is the charge current. We can also, in this equation, replace the value for the drift velocity that we obtained some minutes ago. So if we plug that in, remember that the drift current was minus E over m times the electric field times tau. So putting all that together and manipulating the two minuses cancel and rearranging things a little bit, we get that the charge current through the wire is N sub E, charge of an electron square, times tau, divided by the mass of an electron, times the electric field, times the area of the wire. Now the quantity in parentheses It's called the conductivity. Something to notice here is that the current is equal to the conductivity times the area times the electric field. And if we consider the direction of these quantities, the electric field is a vector that points to the right, therefore, in our example. So therefore, the current through that wire, the charge current, also points in the same direction as the electric field. Now, if you consider that the electrons are moving in the opposite direction, it is a little bit strange that the charge current points in the direction of the electric field. Electrons are actually moving to the left, yet the charge flow is in the same direction as the electric field. So consider this. Suppose that you connected a wire between two terminals, one positive, one negative. So one of the charges of the negative charges of the negative terminal is going to move through the wire, and it's going to end up on the other side. Once it arrives to the other side, it's going to cancel one of the positive charges there. So a negative charge moved from the right to the left, and the end result of this is that one of the positive charges disappeared, got cancelled. So notice that what happened here, one negative charge moving to the left is completely equivalent to a positive charge moving to the right. If a positive charge had moved through the wire from left to right, notice that it would have canceled a negative charge on the right, and that positive charge on the left side would be gone, so the end result is the same. So what we can say is that the motion of negative charge to the left is completely equivalent to the motion of positive charge to the right. So since the direction of the motion of positive charges is the same as the direction of the electric field, then as a convention, because it's easier and you don't have to carry a minus sign or think about the motion of the charges being opposite to the direction of the electric field, since positive charges move in the same direction as the electric field, we're going to consider that when we're talking about the current in a wire, we're going to consider that what's moving is the positive charge, because those charges will move in the same direction as the electric field. And regardless of whether the positive charges or the negative charges are moving, the current direction is the same. It's always in the direction of the electric field. Now the quantity in parentheses, as I just mentioned, has a special name and a letter. The letter for it is sigma, the Greek letter sigma, and sigma is called the conductivity. So the conductivity is, as you can see there, a property of the material. The density of electrons is a property of the material, and the tau, which is the mean collision time, is also a property specific to the material: gold, silver, aluminum, etc., copper. So this quantity, the conductivity, is a different value depending on what the conductor is, which conductor you're using in your wire. Another quantity that is used to describe the current in a wire is what's called the current density. So the current density is defined as the current flowing through a wire divided by the cross-section of the wire. Notice that if we replace for the current the expression sigma A E, then when we divide by the cross-section of the wire, the A's goes away and we get sigma E. This current density is basically what it's telling us is the amount of current per square meter flowing per square meter of the cross-section of the wire. Canceling the A, we get a simple expression for the current density inside a wire. It's simply the conductivity multiplied by the electric field.